The system, we observed a few clips earlier, consisting of a pulley and two masses suspended from the pulley, is called an Atwood machine. We'll let M1 and M2 stand for the masses. W1 and W2, and I labeled those backwards, didn't I? W1 here, W2 here. M1 with weight W1, M2 with weight W2. Now, we haven't really talked about weight, the meaning of weight versus the meaning of mass, but mass is how much, can be measured by how much an object resists being accelerated, whereas weight is the force that would be exerted on that mass, downward force, by gravity. So weight and mass are two completely different things. The two are used in a very confusing manner in most layman's terminology, okay? There's a lot of confusion in this just because people don't seem to understand the difference between weight and mass. In a lot of cases, there's no reason they should, but just make sure you make that distinction. Okay, so we got the pulley, we got the two masses. Gravity pulls harder on one side than on the other. And if there's enough difference in these two forces, that'll be enough to overcome the friction in the pulley. And of course, we observed very clearly that there's a significant amount of friction in some pulleys. In the pulley we used, it was kind of a confounding factor. And we had to, in the case of that demonstration, experiment, or whatever, we had to transfer a lot of paper clips from this side to this side in order to overcome the friction. Okay, so now what about the motion of an Atwood machine? There are several important things you got to know about an Atwood machine. In the first place, the motion of the system is not up or down, because if one side of the system is going down, the other side is going up. You don't have motion solely in one direction or the other. The motion of the system is going to be characterized by whether it's clockwise or counterclockwise. If things tend to rotate counterclockwise, then we actually would take that as generally as a positive rotation. If we do a right-hand rule of counterclockwise direction or motion, remember, we rotate in this direction. If we rotate the x-axis toward the y-axis, positive in the positive direction, we get a positive force in the k direction. You might remember that. Related to that idea, you don't have to make that relationship real specific at this point, but that's clockwise motion or counterclockwise. Counterclockwise is positive, clockwise is by default negative, but you can actually make a choice of positive direction, as you can with linear motion. And you can contradict this, just don't contradict it in a case where you're dealing with torques and moments of inertia and Newton's second law for rotation. We haven't talked about that, and it'll be some time before we do, but that's the convention. The other thing about the Atwood machine, of course, is the net force is the magnitude of the weight W1 minus the magnitude of the weight W2. In this case, that net force would be counterclockwise. Now, that's assuming that there's no friction. If there's friction, then we have minus the force of friction. And the force of friction will be opposite to the direction of motion, so I'm going to have to put a plus or minus on this, and you're going to have to decide from the direction of motion whether the friction acts in the positive or negative direction. Okay, the other thing that's really important that people tend to forget, the entire mass of the system is being accelerated by the net force. Now, if the pulley has negligible mass, then the mass of the system is just M1 plus M2. If the pulley has a significant mass, well, that gets a little bit complicated because some of the mass is toward the outer rim. It gets accelerated at a greater rate than the mass toward the center. But we can kind of think of an effective mass of a pulley. And when we get to an analysis of rotational dynamics, we'll be able to deal with the moment of inertia of the pulley and its effect on the system. The point is, though, that all this mass is being accelerated by the net force. This mass, and if the mass of the pulley is not negligible, what we'll for the moment call its effective mass. If you keep those three principles in mind, you'll have a much easier time dealing with the Atwood machine. Now, what's the acceleration of the system? Well, the acceleration is the net force divided by the mass of the system. What's the net force? Well, let's assume for the moment that the system is moving in the counterclockwise direction, so that the net force is going to be W1 minus W2, where I've left the arrow over the vector off, and the absolute value signs can therefore be left off. So W1 is just the magnitude of the weight of this mass, W2 the magnitude of the weight of this mass. And then it's going to be minus the force of friction. That's going to be divided by the mass of the system, which is going to be M1 plus M2 plus the effective mass of the pulley. Now, I haven't pointed out the note at the top. I'm going to say the pulley has a, quote, effective mass, MEFF, mass effective. Okay, so I've got arrows to this pulley and this pulley. This is just another picture of this, but with a slight change. Okay, so we have this expression for the acceleration of the system. Now, if the system was rotating in this direction, if this mass is greater than this mass, we won't get the system to rotate in this direction by releasing this mass, but we could give the system a push in this direction, and it would slow down. Again, if M2 is greater than M1, or if M2 plus the W2 plus the frictional force is greater than W1. In any case, if we did that, if the system was moving in this direction, then the expression would be the same, except the frictional force would have a positive sign on it. And you can reconcile that with your intuition and by analogy with some things that you should know about the motion of a mass up as opposed to down the incline. Okay, now, the situation that we saw in the previous videos, we were transferring a constant mass from the right side to the left side. In other words, we were transferring mass in constant increments, which I'll call delta M. In the case of that demonstration experiment, the delta M was the mass of a single paper clip, small paper clip, until we switched to the large paper clips. Okay, now, then what we have is, if we originally had mass M1 and M2, then we're going to have mass M1 minus delta M and mass M2 plus delta 2 on this side by transferring that mass from one side to the other. So we're going to have weight 1 minus delta W being the weight of the mass delta M. And on this side, we'll have weight W2 plus delta W having the same meaning. So the question now is, what's the change in the net force on the system? So I'm just going to pause the video for a second. Of course, the pause will seem very brief to you, but I want you to think about that. Okay, well, the net force is going to be W2 plus delta W minus the quantity W1 minus delta W, this force minus this force. That's what I've written down here, and then minus your frictional force from the pulley. And we can rearrange that very easily. let's see if I can stay out of the way of my writing here, W2 plus W1 minus W1 minus the force of friction. And then we have the delta W here, and we have a minus negative delta W here, so that's plus 2 delta W. And the change in the net force, you notice that what we have here is the same as what we had over here. The change in the net force is just this plus 2 delta W. And that's the answer to the question. Now, if you're analyzing a system of that nature where we're transferring masses, you want to kind of take this to heart. Don't treat this as a formula that gets you the right answer. See why the change in the net force is 2 times the weight of that paper clip. And you probably understand that pretty well anyhow.